Hello! You know, if I've got my headphones on, then we're going to be doing a code-it-yourself synthesizer video. And today I thought it would be useful to have a look behind the scenes at what's actually happening. If you've seen any of the videos before, and frankly to enjoy this video to its fullest you probably should have seen the others, we're going to be looking at this mystery file called olcnoisemaker.h, which is a file I've written which runs in the background to handle the sound hardware. You may also notice a beat going on in the background, and that's because I've developed a sequencer which now uses the synthesizer tools that we've already developed to produce this structured drum pattern. It's not a very complicated addition to the synthesizer, so I'll be including it at the end of the video. If you have been using my synthesizer, you'll know that we always include the olcnoisemaker.h file at the top, and this includes the utilities to talk to the sound card and produce sounds. When we start programming with the code-it-yourself synthesizer, the first thing we need to do is create an object of type olcnoisemaker. And we talked about this in the first video, and we also said there were two magic numbers at the end. I think it's time to understand what these two magic numbers are really for. Let's take a step back from the code and actually consider how our code-it-yourself sound synthesizer delivers sound to the speakers, so we can hear it. And I'm going to emphasize that this is an ideal real-time scenario. The synthesizer produces samples, in digital form here, a 16-bit word, to the sound card, which is also known as a DAC or a digital to analog converter, and it takes our digital binary word here and converts a single point of amplitude in the waveform in analog. Now we saw all of this in video 1. However, for all programmers this contains two dreaded words, real-time and ideal. On a Windows desktop operating system, there is no such thing as real-time. So we always have to try and come up with hacks and workarounds to make it appear real-time. And when we're dealing with the real-time, in the real world, things can't be ideal. Other things get in the way and stop us achieving what we want to achieve. This is a more realistic look of the system. As well as my synthesizer application, I'm also competing for resources with Windows via Chrome and OBS and Visual Studio, and knowing my luck, I'm probably mining Bitcoin for some international agency. Which means all of these things are competing for resources on the CPU. And if you're using just the regular Windows Sound Mapper, as we are with the One Lone Coder synthesizer, one of the things we can't escape from is sound is real time. And for our synthesizer, we're typically doing everything at 44,100 Hz. This means we're sending this many samples to the sound card per second. And this is a hard deadline. If we don't match these timings, the sound will sound choppy and broken up. Or it'll sound speeded up like the chipmunks. So what approaches can we take? Let's start off with a really naive approach. Let's take a timer. And this timer is clocked to output the frequency that we need. And the timer generates an interrupt which interrupts Windows, and Windows then goes away and collects all of the information it requires to generate a single sample to deliver to the sound driver. Theoretically, there's nothing wrong with this approach. We know that the samples will be delivered in real time to the hardware. Practically, though, it's disastrous. For Windows to gather all of the information it needs to produce the sample, it has to interrogate all of the processes which are using that particular sound interface. And we're instructing it to do this at 44,000 times a second. That means Windows needs to do 44,000 context switches, where it interrupts the currently running process, stores its state, launches the new process to where it was before, gathers the sound information, stores that process back, and then goes on and on and on. And we're asking it to do this of all processes 44,100 times a second. This is quite unreasonable, and the CPU time required to do these context switches is actually quite significant. We can do a quick calculation to see how much time does the CPU have to produce each sample, and in this case it's 0.2 milliseconds approximately. So Windows has to manage all of these interruptions and data gathering within a 0.2 millisecond window. Well, the most obvious thing to do is reduce the number of interrupts. So what if we set our timer to something a little bit more manageable, say 20 Hz. Clearly in this situation now, we must deliver more than one sample in order to achieve our 44,100 output sampling rate.
Doing a simple calculation, we can see we need to produce 2,205 samples now per interrupt. And this is approximately 50 milliseconds worth of audio.
Creating a packet of audio is just better all round. As each process is switched in, it can go away and generate 50 milliseconds worth of audio. This will result in fewer RAM and cache misses and be more optimal regarding CPU resources. However, it's introduced now one important dynamic, and that's latency. In this case, there will always be a 50 millisecond delay between the process, or the synthesizer in this case, outputting sound, and us hearing it. And latency management is quite important to deal with. In most, say, digital audio workstations, it's probably okay to have a bit of latency. But in real-time situations, say where the player is playing the keyboard, latency becomes a big problem. In fact, if you get over 30 milliseconds, it's very difficult to play an instrument where you press the key and you have to wait 30 milliseconds before you hear the sound. Your brain just can't reconcile that. So we always try and aim for latencies to be as low as possible. It's worth thinking about an embedded system for this approach though. So digital instruments, say keyboards or guitar effects, probably do use this approach of having an interrupt at the sample frequency. But that's okay. In that situation, there's nothing else to interrupt the processor from doing what it's doing. In the real world, we have to live with a bit of latency.
We can modify our drawing a little bit here now. We don't need a timer, because the sound driver can directly tell us when it's done with the sound. However, drivers don't usually like working with shared memory in this way, so it's no good just having one block of samples here, because the sound driver will be too busy sending that through the CPU into the DAC, and Windows will be wanting to fill it at the same time, so we need to have more than one block in this case. What we actually would prefer is a queue of sample blocks. And this is nice because if we assume that the system is now two parts again, like in our ideal system, this side is clocked fundamentally at the frequency that is required to output the sound, whereas this side can be very variable. And it's quite a common technique to use a queue or a buffer like this to cross timing domains. I will add a little disclaimer that this layout that I'm showing on the screen is quite an abstraction, but I believe it gets the point across quite elegantly that when we're crossing time domains like this, we need to think about how we handle the data. And there are things that we have to be careful of. If we output too many blocks, we increase the latency, because each one of these blocks represents a fixed amount of time, and effectively we're looking into the future here. So if I press a key on the keyboard, there'll be a delay of how many blocks are waiting in this queue. On the other hand, if I don't have enough blocks in this queue, I'm starving the sound driver of sound to actually produce.
We can use our synthesizer to explore these effects.
Now I can reveal what these two magic numbers are for. So the 256 is the number of samples in a block, and the 8 here is how many blocks I'm going to make available to put in the queue. So if I go to our ideal real-time scenario, I can assume there is one block with one sample in. This will of course require 44,100 updates per second to produce real-time sound. Let's have a listen. Headphones on. Well, that was terrible, and I apologise if you've just blown up your headphones. What we heard though was just lots of clicks and pops, and that's because the sound card is significantly starved of data. I'm going to start playing it again. And we can see here the latency is increasing. Let's go to the other end of the spectrum. I'm going to say each of my blocks does contain 256 samples, but I'm going to have 1,000 of them. Oh, the sound has just started. So that delay was the latency, about 5 seconds worth in this case. And if I press a key, the key's gone down, nothing's happening. There we go. So this arrangement makes it impossible to play any kind of live instrument. And it's all about finding the correct balance between the latency and the performance. I found that these two numbers work well for most of our applications.
I'm calculating latency by looking at the wall time and the CPU time. So for every sample that gets processed by a synthesizer, we know, we use this dTime variable that you get in your make noise function, we know where we're up to in the songs. That's according to the CPU. But we also have wall time, which is around us. That's just the natural order of the universe progressing through time. In the ideal scenario, the two should be the same. The CPU is always being able to keep up with the wall time. But we may end up with a discrepancy, and we call this latency.
And we can demonstrate the CPU struggling as well. So if I set this to debug mode and start it running, it's going to get a bit noisy and awkward again. We can see, under normal running, the latency is approximately 0. It'll fluctuate a little bit. I'm just going to turn down the audio recording for a second. Hopefully that's not too loud. And if I start to saturate the CPU with things to do, so I'm going to press lots of keys simultaneously, sorry about that, you see it was a dreadful mess, but the CPU had more to do than the time it was allocated to do it, so we increased the latency. And that was because we were also in debug mode. If I send this over to release mode and do exactly the same, you can see it handles it okay.
Let's take a brief look now at the OLC noisemaker.h file code.
The noisemaker.h file uses the Windows Waveout API. It's actually quite a simple API to use, so it's got built-in functions to count the number of sound cards, for example. So my enumerate function does just that. It counts the number of sound devices and then goes through them one by one to get the name and pushes them into a vector. Once we've enumerated the devices, we can create the noisemaker background process. And to do this, we fill out a wave format structure with all of the relevant information of our synthesizer. So it's got the sample rate and how many bits per sample. Now if you remember, this class is a template class, so this is set to short or int or float, whatever data type you want. How many channels we've got is whether we're using mono or stereo. We also provide some information about how our memory is going to be structured that contains the sample data. Once we're happy with how it's set up, we call the Waveout function here, which takes the device ID number and the wave format structure. Next we allocate some memory. These are the blocks in our queue. As far as I'm concerned, the queue is just a big contiguous lump of allocated memory. However, the sound card will appreciate it being delivered to it in chunks, as we've just seen in the slides. So I just allocate the memory in one go here, but then I allocate what are called wave headers, and these are the things that the Waveout API requires to know things about these blocks of memory. So each wave header contains the size of the block and a pointer to where the block is in our memory. So in my big lump of memory, I'm just breaking it up here using some simple pointer arithmetic. Thank you Windows, conveniently, for whatever reason, I have to cast it to type LP string. Anyway, the first thing that the OLC noisemaker does that's active is create a thread. And it runs there in the background. This is what makes it quite easy to work with in subsequent code, because we don't have to worry about what it's doing now. It will automatically call our make noise function as and when it requires data to fill the blocks up with. So let's have a look at the main thread. Fundamentally, it's a while loop, and in this while loop, it waits for the sound driver, the back end, to say, right, please fill this block. You have a block free to fill. But how does it know to do this? Well, when you create the Waveout device, you create a function called a Waveout proc function. You'll see this in all of the documentation. It's always called the same thing. And this function is registered as a callback within the API. So when the API says, well, I'm done with that block of data, please give me the next one, we can increase a counter for how many free blocks of data we've got left. And I use a condition variable here to notify my thread to say, well, you've got a block free now, please fill it with some data. So this unlocks, and we carry on. The block is no longer free because we're going to fill it, so my count of how many free blocks is decreased. I then need to prepare the block for processing, and all this really involves is setting the header to some initial state. I then need to fill the block with the relevant data. Now in my code I have the make noise function, and so for each sample within the block in this loop I call the make noise function along with the current time, so everything can be synchronized. And that's done here, because if you remember in our code, when we create the sound machine, we then set a user function which registers our make noise function. The make noise function is expected to return a value between minus and plus 1, and I scale that to the integer domain then. So even though the user experiences everything with floating point numbers, the sound hardware actually expects a integer format for the sample. So the noisemaker class attempts to deal with all of that behind the scenes. So you can just work purely with mathematics. You can work in the floating point domain or the real number domain if you prefer. In a stereo system, we need to do this for both channels, left and right. Once the block is filled with data, we call Waveout prepare header to tell the header that it is now ready, it is full of relevant data, and we write the block to the queue. The API will handle all of that for us. And that's it.
A similar but opposite process can be used for reading sound from microphones, and we might explore that in a later video. But the Waveout API is really quite simple, and my wrapper file here does make life a bit easier if you're more interested in the functions and formulae behind generating sound. If you do study the source code, you'll see there's some interesting things around static pointers and callbacks, and these are just sort of little hacks and bodges around how Windows can register functions that are actually class members. That said, I believe the code is simple enough for anybody to follow.
As the synthesizer has grown in sophistication, I've made a few changes to the very basics, but nothing that will stop your programs from working completely. The first thing I've done is taken the channel, which was used to signify which instrument should we use. I've changed that now to a pointer to the instrument. So the note structure itself contains enough information to know which instrument it needs to play itself. And so here we have the previous make noise function, where we can see the channel was interrogated each time. This has now changed to a much more elegant approach, I believe, that the note now knows which instrument to use. I think this is quite a nice approach now, because the make noise function has eventually become static. There isn't really any more user code that needs to go into this. And as we're manipulating sounds, really all we're doing is manipulating the instruments.
I thought it would be useful to have notes playing automatically in the background, as you heard at the introduction to this video, so I've created a sequencer.
The sequencer is so simple I didn't think it warranted a video on its own, and that's why I've bundled all that Waveout stuff in at the start. To explain how the sequencer works, it's probably best to have a look at how it's used first. And this is simply it. So I create an object of type sequencer, and I specify the tempo. Now by default it assumes that I'm working with a typical 4 beats arrangement. So I'm hesitating to say the word bar here, but it's basically if we specify a beat, we look at this number here, we've got x dot 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 x dot 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 x dot dot x, and so on. So the beats are the x's in this case, and the sub-beats are the dots. And you get to play around with those later, and this can give you different sort of timing signatures and fields. The sequencer will be given a set of instruments to play. So in this case I've added a kick drum, a snare drum, and a hi-hat. And I specify the pattern I want it to play using just a string. By default this is set to 4 beats and 4 sub-beats. So in total there are 16 elements. And for each sub-beat there is a character that represents whether the instrument should be played or not. If I just simplify it at the moment and take a listen, we can see that the pattern reflects the arrangement of characters. Let's say I saturate the array like this. I think you get the gist of how this works. So the sequencer can have multiple channels, or instruments in this case, and each channel will have its own beat string. In our main loop, we need to update the sequencer with how much time has elapsed since it was last updated. Now this is important that it is wall time, not CPU time. Wall time will provide a consistent sounding beat. CPU time, depending on how busy the computer is, will vary, and you'll end up with a beat that isn't consistent. So to get the elapsed time, I'm using some chrono library trickery. I think the chrono library is one of the most cryptic libraries available out of the standard library, but you can see some of my other programming videos, which should be indicated in the card above, which use this quite extensively for computer games. When the sequencer is updated, it creates a vector internally of new notes to play, and it will return how many new notes there are to play. then the user simply takes that vector and adds it to the list of notes playing throughout the system. You remember vec notes contains all of the notes, so that could be keys, stuff from the sequencer, stuff from MIDI files, any of the other techniques that we've looked at in the past. Vec notes is just a vector containing all of the active notes. So for each update of the sequencer, we want to firstly clear the vector of notes, and we want to accumulate how much time has elapsed, because the time that have elapsed between updates may be fractions of a second. And we only want to do something when the accumulated time is greater than the beat time. So this is how much time needs to pass per sub-beat. It's important that we don't just set faccumulate back to 0 here, because we want to accumulate any residual time left over, or else things will get very messy very quickly. Once we know we've gone over the beat time, we increase the current beat. And when the current beat goes over the total number of beats, we reset it back to 0, so our sequencer becomes a loop. When we know that the sequencer has activated a new beat, we want to check all of the channels to see if the character at that particular beat spot is a capital X. That indicates play the instrument. In which case we create a new note, add the channel instrument to it, we set the ID to 64, which in my percussion set just means play the note as normal, and we add that to the vector of notes that we're going to return. And here we just return the size of that vector to indicate, yep, we've got some new notes, let's add them to the list of active notes playing in the synthesizer. For this sequencer I created 3 new instruments, a kick drum, a snare drum and a hi-hat. I've also added a lifetime variable to each instrument, and this forces the system to switch the note off once that lifetime has expired. So previously you'd press a key and the note would keep playing, and if you lifted the key off, it would then issue the note off command. Now the note off command is issued on max lifetime, so which either comes first, either the note off command is issued or this lifetime expires. And this was needed because the sequencer doesn't issue a note off. And you wouldn't want it to, because sometimes you might want the sounds to overlap slightly. So for my kick drum is mostly a low frequency sine wave with a little bit of frequency modulation, just to give it a kind of sound, and a tiny fraction of noise. The snare is a similar arrangement, although this time not quite as low frequency, and a lot more noise. And the hi-hat is mostly noise, and a slight square wave frequency thrown in there for good measure. So let's play with some of the characteristics of the sequencer. So by default I've got it set to 90 beats per minute. Let's increase the tempo. We can also change the time signature. So I've already created a sequence here, which if we notice, the beat now is every 3 sub-beats. So if I tell it that I've got 4 main beats, but only 3 sub-beats, and we'll just set that tempo back down. We get a different musical characteristic.
So this video has really been about the sequencer and the Waveout API being used in the OLC Noisemaker class file that I've provided for all the synthesizer videos. It's been a bit of an odds and end video, I'm aware of that, but I did want to get these points covered at some point. As usual, all of the code is available on GitHub. Take it, hack it, do what you want with it. If you've enjoyed this video, please give us a thumbs up, it does help a lot, and have a think about subscribing, and I'll see you next time. Run out of keys.